Okay, so let's remember the chain rule for powers. We have the derivative of x to the p is equals px to the p minus 1. And if we use chain rule with a function that is power to the p, then the derivative of that function to the p is p times the function power to the p minus 1 times u prime of x. Now, let's see some examples of how that's going to work if we take different type of powers. So notice this generalized exercise, we have pi to the x, x to the pi, 5 power to e to the x, and x squared minus 7 power to the e. So clear this out. First, notice that when we have pi to the x, pi is still a constant. So I can write this out in expression with the exponential function. So if you don't see it right away, this is something from the type b to the x. So if we take a derivative, this is just going to be pi to the x, but now we're going to multiply by ln of pi. Okay, so this is just something of this form, because pi is still a constant on the real numbers. Now if we go to x to the pi, that's a different thing. Notice that in x to the pi, the variable is x and the exponent is pi. So by law of the powers, y prime is pi x to the pi minus 1. Okay, now the third function, 5 power e to the x, is now a function of the type b to the f to the x. Okay, and so essentially, if we have b to f to the x, this is a chain rule that we can use. So the generalized idea of this will be that the y prime is b to the f of x times f prime of x, since we're doing still a derivative of an exponential. Okay, so let's see in this case what that mean. We have that y prime is 5 to the e to the x, 5 to power e to the x, times e to the x prime, right? Which in this case is going to be e to the x, since the derivative of e to the x is e to the x. Okay. Now, for d, we have y equals x squared minus 7 power to the e. In this case, we have a chain rule situation as well. And this is something of the shape f of x power certain n. Okay, so according to the generalized power rule, this is y prime is n f of x to the n minus 1 times f prime of x. Okay, so in this scenario, e, the Euler number, is just another number. So this is going to be e x squared minus 7 power to the e minus 1 times the derivative of the function inside, which is x squared minus 7. The derivative of that is 2x. So we get 2ex x squared minus 7 to the e minus 1. And that is the general type of situations that we can find when we're doing generalized exponentials. Now, you can always have more complicated situation. For example, something like y is and a combination of the two things. You can have x squared minus log of x power to the x squared. Okay, so power where both of the things are functions, and for that we can explore what happens if we use the logs. Okay, so we apply a log on both sides. Notice we can use the property of the exponent in here. And now we got the log of y is equals to x squared log of x squared minus log of x. Now we can take derivative on both sides. Derivative of this is now going to be an implicit function, and this is 1 over y times y prime equals, and then this is a product rule situation, 2x log of x squared minus log of x, and then plus x squared, and then the derivative of this, which is a big chain rule, 1 over x squared minus log of x times 2x minus 1 over x. Okay, and at this point we're not done yet. Okay, to find out y prime, we get to do all this whole thing over here, but now we multiply that by y. So y times all this, and then we replace y by the original function. So this is one of those cases where we have a very large function going on. Okay. Now notice at the end, y prime is going to be this times this. And so here we're not only using the properties of the powers, but we're also using the properties of the logs. Another quick example will be what happens if we have something like phi to the x squared minus 7. Remember that this minus 7x. Remember that this is still something that we can work with chain rule, and the derivative of the exponential is itself. But now we need to multiply by log of 5 because this is that base, and then by the chain rule, which is 2x minus 7. Okay. Now, the general derivative for a base b of any log is going to follow pretty much the same properties of the log, but now, similar to the exponential of base b, we're going to need to multiply by a factor of log of b. Therefore, the derivative of log of b of x is going to be 1 over x log of b, and the derivative of log base b of the absolute value of x is going to be 1 over x log of b. Of course, in this case is when x is positive, in this case is when x is different from 0. Okay. Now, we can have a lot of functions where we have exponentials where the base and the exponent are variables, and they're not very easy to deal in terms of a tangent line. So take as an example this function f of x equals x to the x. Turns out that when we find a tangent line in the point 1 over e, we're going to get that it's also going to depend of the Euler number. And the reason for that is the following. So if you consider y equals e to the x to the x, there's a couple of things that you can do to manipulate this. So you can take the log of y, and so log of y is log of x to the x, or x log to the x. But now instead of writing this and taking the derivative here, I'm going to take an exponential. And remember that the exponential and the function cancel log cancel each other. So we're having e to the log of y is e to the x log of x. So now we have that y is e to the log of y, which is e to the x log of x. So notice that what this is telling me is that I can express x to the x as e to the x log of x. Okay, so I can always represent a power function that has both exponent and base variables as something with constant base, the Euler number, and then exponent in terms of variables, like here. So this is going to help out a lot, because this tells me, okay, so y prime is the derivative with respect to x of this, and I know how to manage exponential function, and especially the Euler base. So I know that this is just going to be the same function, and then I have to multiply by the chain rule, which will be log of x plus x times 1 over x. So that will be e to the x log of x times log of x plus 1. And so that is telling me that the derivative of x to the x is just essentially going to be x to the x, which is the same thing, times log of x plus 1. Okay. If I plug now in a point like 1 over e, notice that I'm going to get e to the 1 over e log of 1 over e, okay, times log of 1 over e plus 1. Notice that this log of 1 over e is just essentially minus log of e, so minus 1. Okay, and provided that, then that means that this is just going to be e to the minus 1e times, and this is going to become minus 1 plus 1, which is 0. Okay, so that means that we have a flat slope of the tangent line, which makes sense with this. We have a flat tangent line over here. Okay, and so we could pretty much get the solution of the tangent line in that point if we're using the point 1 over e. We get y minus 0 is 0, x minus 1 over e. So that implies that y equals 0 is the y equals 0 is the tangent line over here. Wait a minute, I'm using incorrect in incorrect way. This is not going to be 0. It's 0 in the derivative. This is going to be minus f of 1 over e. So whatever f of 1 over e is, which is 1 over e power 1 over e. That's not 0. Okay. All right. So now let's take a look to some other examples, mix and match of what we can do now with these tools. So y log base 2 of 2x plus 1. B is going to be y x to the sine of x. And c f of n is n log of n. Alright, so the first one is just log in a different base. So we just gotta apply the formula, and y prime is just going to be 1 over whatever the function inside is, but I gotta multiply here by the log of 2. Okay, that's just the regular thing, but now I gotta multiply by chain rule, which is the derivative of 2x plus 1, which is 2. And so that's it. This is just going to be 2 over 2x plus 1 log of 2. Applying directly the formula of the derivative of a log for base b. Now, let me use the space first for c, and then I go back to b later. F of n equals n log of n. Doesn't have anything special. The only thing here is that we're showing that this can go with different variables. And here we're using as our continuous variable just n. And so f prime of n is just going to be a product rule over here. This is just 1. And remember, log of n is just log base 10. So if I multiply, and if whenever I take the derivative here, this is just going to be 1 of n over n log natural log of 10. Okay, and that's the only special thing about this particular case. Now in b, I have an exponential x to the sine of x. And so just like I showed you before, I can actually go ahead and transform this in the exponential form. So I can say, okay, so log of y is log of x to the sine of x, which I can write as sine of x times log of x. But, or I don't even need to do this step, to be honest. I could do the logarithmic derivative, but I can just rewrite again y as the exponential of log of x sine of x, right? And so that is e to the sine of x log of x. Okay, so now I just rewrote this as an exponential, and now I can take the derivative. Y prime is the same exponential, e to the sine of x log of x, times chain rule, and chain rule here is a product rule, cosine by log plus sine times 1 over x. Okay, and so at the very end, the derivative of x to the sine of x is x to the sine of x times cosine of x log of x plus sine over x divided by x. Okay, so this special case is a little bit more involved in what you have to do. Now let's use one scenario where actually doing the full logarithmic differentiation by implicit differentiation will make more sense. So sometimes product quotients and power functions are differentiated where they're corresponded with their corresponding rules, but sometimes the direct computation of that is going to be very tedious. This example showcases that complicated a step that we have to take. So imagine this: we have a power to the 4 product rule with a square root, quotient rule with x squared plus 4. So this is a gigantic derivative in terms of a quotient rule with a bunch of chain rules. Instead, what we're going to do is we're going to use the log, and we're going to simplify the calculation of this situation. Okay, we're going to have f of x is x cubed minus 1 to the 4 square root of 3x minus 1 divided x squared plus 4. Okay, now we're going to apply the log, the ln of f of both sides. So ln of f of x is going to be equals to ln of x cubed minus 4 root of 3x minus 1 over x squared plus 4. And you can imagine what comes next. I'm going to write this by properties of the log. So this is going to be log of x cubed minus 1 3x minus 1 minus log of x squared plus 4. Okay, and then using here, this was using quotient rule of logs. Now I'm going to use product rule of logs with this, which is log of x cubed minus 1 to the 4 plus log of 3x minus 1 square root. Okay, or square root of 3x minus 1. Now this square root can be seen like a power to the 1/2. So now this can look 3x minus 1 to the 1/2. So at this point now I can use the properties of the exponent. So now this is 4 log of x cubed minus 1 plus 1/2 log of 3x minus 1 minus log of x squared plus 4. So this is a lot of work of rewriting. But notice that now when I'm going to take the derivative, it's going to be really simple. Derivative of log of f of x is going to be f prime of x divided by f of x. Okay, and on this side is going to be just 4. The derivative of log of x cubed minus 1 is going to become 1 over x cubed minus 1 times 3x squared from the chain rule, plus 1/2. The derivative of this is 1 over 3x minus 1 times the chain rule, which is 3, minus 1 over x squared plus 4 times the chain rule, which is 2x. Okay, so now it does get simplified, because now I can just write f prime of x equals f of x, which is this, times this. So I can write this as 12x squared over x cubed minus 1 plus 1 over 2 3x minus 1, and I can write a 3 over here, and minus 2x over x squared plus 4. And then again, later you can write what the original f of x is over here. Okay, but I can find the derivative in terms of the original function plus something else. And so this is one of the advantages of using this technique. Doing the derivative right away with product rule, chain rule, and quotient rule might be equally cumbersome in some cases, so you have to decide what tools suits you better.